Well, I'd like to, I'm Jack Dongera, part of the Top 500 team, along with Eric Strohmeyer, and Wu Fang is representing the Green 500, and we're here to present the Top 500 BoF. The Top 500 BoF has been going on here at SC since 1993, so that's 32 years of doing this. This is for the Top 500 list. This is actually the 64th list of the Top 500. As you're probably aware, it's also, the Top 500 is also presented at the meeting, the ISC meeting in Germany. So today we have a schedule which, I should move the slide forward. So today we're going to first present the awards for the Top 500. We'll talk about the student cluster competition. Brannis from Livermore will talk about the El Capitan #1 system, and Rio Yokoto will present some really exciting algorithmic development in terms of a fast way to do matrix multiply, and that'll be followed up by Eric's traditional talk about the highlights from the Top 500. So I'd like to start by giving the Top 500 awards, and the order for those awards are going to be something like this. We're going to go through the Top 500 list and hand out the #1, 2, and 3 award, the #1 in Asia, the #1 in Europe, followed by the 1, 2, 3 for the HPCG benchmark, followed by the HPL MXP benchmark, and then the Green 500 awards will be handed out by Wu during the Green 500 BoF, which occurs Wednesday, this time Wednesday. In this room? We're not sure. Okay, it's in some other room. So with that, let me just move on to the presentation. So the #1 computer is El Capitan from Lawrence Livermore at Lawrence Livermore National Laboratory. It's an HPE system which has a Cray interconnect. It's operated by the Department of Energy and NSA, and they achieved a whopping 1.743 exaflops in 64-bit arithmetic. And coming up to receive the award is Brannis and also Trish Dam-Kroger. Trish, good to see you. We'll give you a handshake too, sure.
Certainly.
And we hope there's a photographer. Okay, very good. Thank you so much. The #2 award is going to Frontier. It was the #1 award for a number of sessions of the Top 500, and that's another HPE system along with a Cray interconnect. It achieved 1.353 exaflops in terms of performance, slightly more than they had last time as a result of an enhancement. And coming up to receive this award is Bronson Messner and also Fei He, as well as somebody else. Somebody from HPE, of course. That's right. Congratulations. Congratulations. Next slide. Thank you. Yeah, I get it. Okay, so in addition to the Top 500 award for running HPL is the HPCG award. They were #2 for its performance, and the HPL MXP award, which they were also #2. Thank you. Thank you so much. And the #3 award goes to Argonne National Lab for Aurora. It's an Intel system with a Cray interconnect. It achieved 1.012 exaflops for its achievement. And Susan's coming up along with Chris, along with Chris. And I don't have your last name, Chris. Your last name is? George. Chris George and? Tim Austin. Okay, very good. Congratulations, guys. That's right. So we should move down just a little bit. And this is from me. Oh yeah, thank you. I'm not doing my job, and that didn't work. There we go. Congratulations. The next award goes for the #1 system in Asia. Perhaps no surprise, it goes to the Fugaku system. It's a Fujitsu-based system run out of Riken and Riken Center for Computational Science, and Satoshi Matsuoka will come up to the stage and receive the award. In addition to the top 500, they also achieved number 1 for HPCG award. Congratulations again, Satoshi. Coming to Europe, the number 1 system in Europe is the HPC S system. It's in Italy at Fiara, Italy, and coming up to receive the award is Sergio and Mario, as well as a whole group of people, it looks like. Okay, so we're overwhelmed here. Achieving 478 petaflops. Congratulations, this is your first time on the list. Very nice, very nice to see you. Good to see you again. Hello, good to see you. HPC 6. So why is it 6? What's the?
Because they had 5 systems before.
Before, I guess so. We should move over here, yes. You should scoot down just this way here. If you can, go this way, a little bit more towards Eric. She'll have a wide lens. Thank you so much. Congratulations again. Good job, guys. Nice to see you. Good to see you again. That's right. Good to see you. Thanks, John. Nice. Good job. Our next award goes for the number 3 system, Lumi, which is receiving the award for HPL MXP. They achieved 2.35 exaflops on this benchmark. And I don't know who's coming up. I don't think I saw Chemo. Is Chemo here? No, okay, sorry. Petra. We should look over there. This one here. Very good. Congratulations. And as we, oops, is there a way to go back? Oh, there it is. As was mentioned, the Green 500 Awards will be given out by Wu Fang, and that'll take place tomorrow. And look forward to seeing you there so he can present those awards. Okay, coming up next is the SC Student Cluster Competition. This is a very impressive competition that's been going on for a number of years. It involves undergraduates putting together clusters. There are usually 6 students, plus an advisor, plus the vendor. So they contact vendors to get equipment and put it together and develop a system. That system has some constraints in terms of the amount of power that's required. It has to be below a certain amount of power. During the competition, the teams are constrained by 4.5 kilowatts, and any individual node may not consume more than 2 kilowatts. And there's a set of benchmarks that have to be run, HPL, the NAS parallel benchmarks, ML perf, and a number of other things that take place. If you've not seen the Student Cluster Challenge groups working, I would encourage you to do that. It's in the exhibit floor. Their teams are there working away tirelessly on their benchmarks, trying to get things to run correctly. And we can report that overall, 5 of the 11 teams achieved an HPL score above 192 teraflops. And 10 years ago, that would have achieved a rank of 329 or higher on the top 500 list. So the winner for the HPL was running an NVIDIA system, which had 8 NVIDIA Hopper boards, along with 32-core AMD system, consuming 4.36 kilowatts and achieving 236 teraflops. And that's the Nanyang Technical University out of Singapore. Are they here in the audience? The student cluster? There they are. So stand up and be recognized. Thank you so much, and thank you for your efforts, and look forward to seeing the finals for that competition. Next up, we have Brannis is going to tell us a little bit about the new #1 system on the top 500, El Capitan, and I'll let him take it away, although the next slide doesn't look like his slides. We'll see if we get that right. So did you give them your slides? Here they go. Okay. Very good. The floor is yours.
Right, very good. Good evening. So, yeah, I seem to have clipped the first. How do I go back? There we go. All right. So, yeah, I'm going to tell you about El Capitan. I'm going to really focus on kind of the node architecture because I'm going to be brief, and you know, there's only so much I can cover in a short period. But I also want to say, like, so in my opinion, we have the world's most beautiful computer. So yeah, if you're not familiar, El Capitan is the rock face in the center of the photo on the machine. It's in the Yosemite Valley, so in Yosemite National Park. So the system has a peak of 2.7929 double precision exaflops with a per node peak of just over 250 teraflops. I'm going to talk a little bit at the end of what I have to say about how we measure peak because it's gotten complicated, all right? And I'll talk about it then. The system peak power is 34.8 megawatts. It doesn't take that much to really run run things. The LinPack run was under 30 megawatts, so definitely achieving the 20 megawatts per exaflop delivered. Let's see. So yeah, the big, the most important thing is that the processors are kind of a very new design. The AMD MI300A APU, which combines CPU cores and GPU compute units on the same package, and I'm going to tell you a lot about that. And of course, it's using the HPE Slingshot interconnect that's used in several other systems, including Frontier and Aurora. We've actually had very good experiences so far with Slingshot. There are still some secrets that you have to learn, and we're learning them, and I think we're finding that the network is now working very well for us. In general, the project has started in 2018, joint under Coral 2 with Oak Ridge, and we funded a lot of different activities for HPE and through HPE AMD that really make a difference in what the system provides. A big difference between frontier in El Capitan is that we do not use CrayOS. We use TOS, the TriLab operating system software, which is a Red Hat-based system stack. And it's been developed at Livermore and the other NNSA laboratories, Sandia National Laboratories and Los Alamos. We also include a near-node local storage solution that's called the Rabbits. The Rabbits have no figuring into the LinPack performance, but they are a significant addition to the system. I'm not going to talk about them more because I can go on about them for quite some time. Those of you who have heard me go on about them for quite some time would know that's true. But I'm happy to talk about them if anybody wants to ask me questions afterwards about the Rabbits. And so I'll leave that at that. All right. So the MI300A, it's, as I mentioned, it combines CPU cores and GPU compute units. They also share a unified on-package pool of physical memory. So our processors all use the same HBM3 memory in order to compute, whether you're using computing on the CPUs or the GPUs. You're not using slow through from a CPU through the GPU package to get to the HBM. It's equal access whether you're from a CPU core or a GPU compute unit. It makes the system a lot simpler to program. It makes a huge difference in terms of how well our application teams can use the system. All right. So this gives you a real picture of what the APU is. So for our friends from AMD, what I learned when we started down the road of we're going to use the MI300A, I thought, okay, getting those 5 nanometer GPU chiplets was going to be the hard part. What I learned was that the most important and most difficult part of building an APU is actually that I/O die. All right, and the kind of trick here is that, one, you have to be able to get power through those I/O dies up to the other chiplets, which is pretty complicated. And you also have to be able to get data moving very quickly and have those 4 I/O dies function effectively as a single chip, all right? Because they're basically stitched together at the edges. But so you have 4 I/O dies that they include the interfaces to the 8 stacks of HBM3. It also has a 256 megabyte last level cache that provides, again, significant benefits because there's equal access whether you're, again, accessing memory from a CPU core or a GPU compute unit. Then there are 6 XCDs, which are accelerator complex dies. We all think of them as GPU chiplets. And then the CPU complex die, or CCD, is where the CPU cores live. There's 8 Zen 4 cores per chiplet, so each of the APUs has 24 CPU cores. And as you can see, we get 8 physical stacks. They're 8 high on the MI300A, giving us a total of 128 gigabytes of memory per APU, so 512 gigabytes per node. All right, here is a picture of one of our compute blades. This is 2 compute nodes. So in this picture, you can think of it as a left compute node and a right compute node, although they're really kind of front and back compute nodes the way they slide into the cabinets. You can see 2 of the 300As, and then on each of the compute nodes, and then 2 other compute nodes are there underneath the riser cards, on which on each of those riser cards you get 2 slingshot NICs. So you get 4 slingshot NICs per compute node. it's important to realize that although it looks like you maybe get unequal access, one of those NICs is connected to the adjacent MI300A. So it's actually, each of them has kind of a preferred NIC, each of the APUs. All right, and then, there we go. Final slide. This gives you all the details, or at least all the details that I could fit onto this one slide. And you'll notice I'm actually listing 4 different systems. So we have 4 NNSA 300A based systems. We have El Capitan, which you've heard a lot about already. That's the #1 system on the top 500 this time. Tuolumne is a system that will be an unclassified system at Livermore. It's a multi-programmatic and institutional computing system, so it's shared amongst several programs at Livermore, including, again, ASC, which is the program that funded El Capitan, and the owner, the program which El Capitan serves. That has, so El Cap has 11,136 nodes. Tuolumne has 1,152 nodes. It actually finished number 10 on the top 500. So, you know, we say, oh, it's the smaller version of El Capitan, but it's a 208 petaflop system that is larger than our existing Sierra system, which was the largest system at Livermore prior to these 2 systems. And then there's El Dorado, which, as it says there, is a system owned and operated by Sandia National Laboratories at their Albuquerque site. That's a 3 compute cabinet system, so it has 384 compute nodes, and that was ended up as number 20 on this top 500 list. And then finally, we have a 1 cabinet system that we call RZ Adams, and that's also on our unclassified network, and that's 128 nodes, and it's actually its performance is good enough for 49th on the top 500. Anyway, so I've got various other statistics there for you to take a look at. I find it amusing that we ended up with 44,544 APUs on El Capitan. It's a Paladin drone, right? You know, so when I first saw that, I said, this has got to be good fortune for us, you know, and it's proven to be. With that, I think I'm really ready to wrap it up.
We could take questions later at the end, right? So next up is Ryo Yokoto. Ryo is a professor at Tokyo Institute of Technology, and he is going to be talking about some, I think, rather exciting work, innovative work in terms of algorithmic development for matrix multiply, double precision using integer units. Sorry, did I take up your?
All right, thank you, Jack. So today I will be talking about some of our work we did with emulating DGEM using tensor cores. So of course, we know hardware design is now driven primarily by the huge AI market. You know, GPUs are now exceedingly making use of these low precision units. And they're very good at doing gems. And so how can we use, the question is, how can we use this for science, scientific computing? And there are 2 things we need to work on. One is recovering the precision, and the other is to reformulate our problems into gems. So, you know, the problems that turn in naturally into dense matrices are rather the minority. We have a whole bunch of applications that are not matrix multiplications, but we are now looking into ways to turn them into matrix multiplications. The 2 works that I have shown here are assuming that we already have the problem formulated as matrix multiplications, and they aim to recover the precision. So the first one shown on the left is about recovering single precision, SGEM, from FP16 tensor cores. This uses compensated summation, a technique that's been well established. Kahan summation is one of them. And then this alone does not recover the full accuracy as shown in the leftmost figure on the bottom. You also need to change the default rounding that's done inside the tensor cores, do the rounding outside so that you don't do the round to 0. Instead, you should do the round to nearest. The one shown on the right is recovering DGEM, double precision matrix multiplication from int8 tensor cores. So this is a work that was done with Professor Ozaki, who is the developer of the Ozaki scheme. So there's an algorithm that further splits into many, many int8s. So I'll show a little bit of how this is done later. But first, let's see how the trend of, for example, NVIDIA GPUs has been in the past couple of generations. So you see here in the gray, Volta, in the sort of pink, Ampere, and yellow is Hopper, and green is Blackwell. And it's showing the precision starting from the left, double precision, single precision, and then TF32, FP16, and so on. And you see that the capability of the tensor core units that do FP16 or BF16 and FP8 have been improving quite rapidly these couple of generations. But the FP64 performance, for example, going from yellow to green, you don't actually see an increase. So this means if your code is only computing in double precision, and in particular, if you're doing matrix multiplications using DGEM, the native DGEM function, then you won't see any performance improvement going from Hopper to Blackwell. And so what can you do? You can go and so the first method I described in the previous slide was doing element-wise place splitting. So compensated summation splits the matrix into 2 elements. But in this case, so each element in the matrix could be split into any number of bits. And you can use that to express the mantissa. So in this case, only the mantissa bits are split, right? And you're basically using many lower precision types to express the mantissa bit of the higher precision types. The shared place splitting shown on the right is a little bit different. So it's sort of a shared exponent approach where you share the same exponent among the elements. So it's not an element-wise splitting. Depending on how you group these shared exponents, you can save a lot without losing too much precision. And also, this means that not only the mantissa, but the part that's usually expressed as the exponent, part of it is actually converted to the part you're expressing using, for example, int8. So you can use this, of course, to for any type of matrix, but you can very easily see that the dynamic range that this can handle is a restriction. So we show in these results for so the different numbers of phi in the bottom right figure represent different dynamic ranges or the different number of exponents. And when you increase the exponent range, of course, we need to use more splits to get the same accuracy. And then when you apply this to LIMPAC, so how many splits do we need is the question. How many int8s do we need to express a proper double precision element, or in terms of the shared exponents? So the red line is the HPL tolerance. So you can see that 5 splits on the left figure is barely above this tolerance, but if you go to 6 and then 7, this is below the HPL tolerance. If you go to 8 and 9 splits, you can see that it is as accurate as the original HPL. And you can also see the effect of increasing number of GPUs and basically growing the problem size. You can see that 7 has a little bit of discrepancy, but 8 splits and 9 splits, you can't really tell the difference between the original HPL. So how does that convert to performance benefits? So this shows this relative speed up with respect to FP64 DGEM. So that's shown as 1 here. And then for each matrix dimension, of course, the larger matrices benefit more. And you can see a larger speed up. For example, if you're using S equals 8, that's at the bottom here, you can get roughly up to 2 times speed up. If you're using S equals 5, you can get more than 4x speed up. But S equals 5 doesn't quite give you the required tolerance for HPL. Another trend is, so the important thing is not just the flops that you get. If you're doing so many extra operations, then yeah, of course, getting high flops might be, achievable. But in the end, how much extra power are you consuming to do that? So this shows the performance per watt for the emulated versus native HPL. And you can see shown in the green is the emulated version. And we get better performance per watt. So it's a greener solution to achieve on the Blackwell B200s. You can see that we not only get better teraflops, but we get better gigaflops per watt here. And these are the absolute numbers that you may have seen the relative numbers, but these are the absolute flops and gigaflops per watt that you're seeing here. Okay, so of course, HPL is a well-known benchmark, and it's good to establish that we can actually get the, satisfy the residual tolerance for that benchmark. But how does this work on actual applications? So NVIDIA has kindly provided these slides. So actually, I should have mentioned this earlier. All the slides that have a black background were provided by NVIDIA, and they say NVIDIA at the bottom corner. The ones that have a white background were my slides. And so you can see here a wide range of applications: DMRG, Quantum Espresso, and Berkeley GW, and also QSolver N. So for these applications, you can see that different number of slices that are shown in S are required. So for example, DMRG, it says for S equals 2, it diverges. You typically need 6 and 4 slices. Also, Quantum Espresso, roughly 6 to 7 slices. Also, Berkeley GW, S equals 7, so 7 slices, yields a difference of 10 to the minus 14. So roughly, if you use 6 or 7 slices to express one double, then you can get the satisfied, the sort of satisfactory precision for all of these applications. Finally, I'll show a little bit of detail for each benchmark, but I'll go really quick. So yeah, for S equals 6, it reproduces FP64, S equals 4, generally acceptable, and then S equals 2, the error becomes unacceptable. So this is for the DMRG application. Also, if you go to, so this is for the QSolver D, and the dense QR basically gives you this kind of tolerance. So as you can see here, S6, 7, and 8 slices give you this kind of relative residual. And all of these are far below, well, not far, but significantly below the threshold. So it means these numbers, 6, 7, and 8, are typically the ones that you want to use. Okay, so I think this is my last slide. I hope I didn't go too over time. Thank you very much.
We'll have time for questions after, yeah. And next up is Eric Strohmeyer, who will give us a summary of the current top 500 list.
Thank you, Jack. Good evening, everybody. Thank you for coming. Thank you for staying. It is my pleasure to give a brief overview of some of the highlights of the new top 500 list, which has been published today. I'm going to talk about the various top 10s according to the different benchmarks and criteria we use to create lists and to rank systems. I'm going to talk about new systems in the list, what's exciting and new. I'm going to talk a little bit on a tangent about the market of hyperscalers and the buzz which is there in terms of how many gigawatts they want to install and things like that. I'm going to reiterate some of the observations, continued observations about the changes we see, technological changes in the list. And I'm going to show some of the traditional statistics about the market, focusing just on the systems which were installed during the last 12 months, during the last year. That's 95 new systems on the list. So top 10, we already handed out the awards. As usual, in yellow, you see the changes compared to June. We have a new #1 system, the El Capitan system at Lawrence Livermore National Labs. And Brownies already gave a presentation about it, so I don't need to talk about it in great depth anymore. The #2 system, Frontier, the previous #1 system, and the first exascale system, which we had on the list, did a slight remeasurement. So their LIMPAC benchmark score improved a little bit, but it didn't change anything on their ranking. Aurora didn't get around to submit a new measurements, so they stay in position #3. Those 3 systems are the 3 exascale systems we're aware of, we have on the list. It's remarkable that all 3 of those are installed at Department of Energy National Labs in the US, which is really a sign of the success of the exascale project the department was running for a long time. And of course, not just the systems themselves, but all the science being done on them. The other new system already got an award, the HPC6 system, which is installed at a commercial customer, integrated energy company in Italy. I believe it's the highest ranking system in Italy, not just on this list, but probably ever. And it is, we now actually have 2 systems from Italy on the top 10, which is very unusual. In the past, sometimes there was the question, where is Italy in Europe? Well, right now, Italy in Europe is on top. So that's nice to see. The ALP system, another system in Europe, was enlarged. They have more hardware, and they submitted a new measurement, which allowed them to move on one spot. They're now ahead of LUMI. They used to be behind LUMI, but it wasn't enough for the biggest system in Europe. And the #10 system, the last new system on the top 10 was already mentioned, 2 Alumni. That's the sister system to El Capitan, just a factor of 10 smaller, but still large enough to be on the top 10. So the second system from Lawrence Livermore and the 4th DOE system in the top 10 right now. So that is the traditional ranking ranked by the HPL LIMPAC benchmark. And for a couple of years now, we're collecting benchmark data for other benchmarks, which all of them have been created by Jack. So the second one I'm going to show is the HPCG benchmark. And first thing you might notice is there is no yellow on that slide because there was no change. So we didn't receive any new numbers for HPCG, especially not from El Capitan or from Aurora. So nothing changed. Or to be more precise, the only change you can't see is actually a system called Summit, which is no longer there. Because Summit was decommissioned, unfortunately, last week. And because our deadline was today, our key date was yesterday. It wasn't installed yesterday, so we removed it from the list. It's no longer there. But it's a very important system in terms of history of the list and things like that. That's why I wanted to mention it and call it out again. So no big changes in HPCG, and of course we always use this opportunity to encourage people to actually measure those very important benchmarks and submit them because they provide a lot of additional information in addition to the HPL score. The third benchmark we have been tracking much more recently is the HPL MXP benchmark, mixed precision benchmark, and we handed out the awards for that one too. They were the old #1 and 2, both of them got around to remeasure their scores, and both of them improved them, but because both of them did it the same way on the same amount, actually the ordering didn't change. So still Aurora is the #1 on the MXP benchmark with an HPL equivalent performance of 11 exaflops. So this is not an actual performance you measure in the system. This is the performance a system with full 64-bit arithmetic would need to show to keep up with the mixed precision benchmark on that system nowadays. So it's not an actual performance, it's an equivalent performance, but it really shows not just the potential of the machines, but it really shows the potential of the algorithmic technique of using mixed precision algorithms. And Rio gave a very nice talk about how to push that forward by just ditching the floating point, the point altogether, and just going basically to integer and trying to do it with integer arithmetic. And it is something we see becoming more important in the future, because there is that little market for AI system, large language models, and those guys, they are happy with reduced precision, and they are pushing the hardware vendors into the corner of investing more on the lower precision end and less on the 64-bit precision end, and that might force us to use this type of algorithms in the future more and more. So these three tables I just showed, they show you ranking by benchmark score, which is a ranking by size of systems, so you really see the large systems. We have been doing for a couple of years now, together with who pioneered that field, and energy efficient ranking as well. The energy efficient list at the top 10 here is compiled a little differently. First, there is a level of entry, which simply means you have to be in the top 500, otherwise we're not going to list you. And the second one then is that we actually list you by the ratio, how many gigaflops you get out of the system by using a certain type of watts, electrical watts. So it's a ranking by technology, which means smaller systems actually have an advantage, and which means this list is very dynamic. There's a lot of yellow there. The number 1 system is actually the same as in June, the JEDI system in Europe with Grace Hopper technology, with a very impressive 72 gigaflops per watt. That's way above that 50 megawatt line, which we need for a 20 megawatt system, exascale megawatt system. But the numbers in the right column, if you look at the power efficiency, they are actually all very high. They're all above 62 in the top 10, which is very nice to see. There are a couple of new systems, Romeo 25, Ad Astra, integrated by different companies. You see Evidence systems, you see HP systems and others. The ones I want to call out, the things I want to call out here is if you look in the accelerator column, the second from the right, you see all these systems use some sort of an accelerator, and most of them, actually 7 of them, no, I'm wrong, 6 of them use NVIDIA chips, mostly NVIDIA Grace, 1 and H100, and 3 of them use the AMD MI300A. That's the chip which sits at the heart of El Capitan, and Bronis talked about it, how that chip is designed. So we see a lot of that, and the number 10, the last system in this power efficiency list, is actually the RC Atom systems, one of the sister systems to El Capitan, which Bronis just presented. So you see El Capitan is leading edge technology in terms of power efficiency. The one in the middle, JETI, I also want to call out, because that is the first module, first or second module of the upcoming first European exascale system. So they're also building an exascale system in Jülich in Germany, and it's also built on very energy efficient technology. So with that, a little tangent going towards hyperscalers, but before I do that, I basically plot one slide about power efficiency. And what I did is I just took the power efficiency for the systems for which we have data, which is about a quarter of the systems, and averaged that by system. I also averaged it by RMAX, and I averaged only the new systems. I did this study a couple of times, but it all comes out to about the same, so I just showed the simplest case. And you see I used the logarithmic scale on the vertical axis, which means we see actually exponential growth in power efficiency. It's very nice to see. Exponential growth is always a little tricky to see, especially with the naked eye, but it looks like a very nice curve. So power efficiency grows exponentially, and then there is hyperscalers. Hyperscalers, they're on the news because they are talking about multi-gigawatt data centers. So I actually Googled and tried to look up the definition of a hyperscaler, if there is one today. And companies like IDC do definitions for that, and tried to compare it with the top 500, tried to compare it to the top systems, and I tried to compare it to the total top 500 overall. So a typical hyperscaler system nowadays is supposed to have a floor plan of 5,000 square feet, which is, we easily have that in our large systems. 5,000 nodes, we easily have that in our systems. And depending on source, I say between 20, 40, or even 50 megawatt. So there we are at the edge of there. We are very energy efficient. The largest numbers of measured electrical consumption in the top 500 is 30 to 40 megawatt. But that is measured during the HPL run. That is not nameplate. Well, of course, in all these hyperscaler discussions, they only look at nameplate. So if you add all the storage devices, all the cooling, the PUE of the facility and stuff like that, which may be something between a factor of 1.5 or 2, be generous, then the largest systems we have certainly qualify as hyperscaler by today's standards of that industry. So that's nice to see. We are not the small boys. We can play in the big league. But the question then, which begged me really, is how big is the top 500 overall? And because we don't have power numbers for all the systems, I cannot just add them up. So I did it backwards. I used the last slide, which is an exponential curve for the power efficiency. I used the curve for the total or max installed Limpact performance in the list, which is also an empirical exponential. And because power efficiency is the ratio of those two, I divide them. So your statistic professor probably would slap me on the head if he heard that I was going to do that. Two empirical exponential curves and divide them. So things can get very shaky if you do stuff like that. But if you just look at the math, if you divide two exponentials, you get an exponential, and the exponent is the difference of the old growth rates. If there's something else, then an exponential comes out, something very interesting must be going on. So without further ado, this is the curves I'm actually dividing on some arbitrary scales. They look almost parallel, but not quite. Power efficiency grew on that slide about a factor of 200, while HPL performance during that time frame grew a factor of 1,000. But they almost look parallel, and if I divide them, I get something which I have to plot on a linear scale, because it's clearly not exponential. At best, it's linear. Maybe there is two linear functions in there with an E, but it's certainly not an exponential function. So what that makes me believe is that I actually got my picture, my cause and effect the wrong way around. The size of the system, so clearly power efficiency is technology, is the mediator. But the cause, the driving force, is not how big the systems are, but how much power we can afford to put on the floor. And if we take that, how much power we are willing to pay for during the lifetime operation of the system, and how big our floors we can afford, and combine that with power efficiency, then we arrive at the size of the system we put on the floor. And that ties into this discussion about technological change, that we have seen the whole community slowing down in performance growth overall. And I believe that really is driven through these effects of power efficiency and power budget, that if power efficiency doesn't keep up and the power budget doesn't go up strongly enough, then the systems are not going to grow much anymore. So the nice endpoint, and that's why I did the study, is right now we have about roughly 5, the math there is a little shaky, and you see that the dots are wobbly. We have about 500, 600 megawatts of HPL performance in the list. With the PUE and all that added, the whole list is about 1 gigawatt. And that puts some perspective on a hyperscaler saying they want to have multi-gigawatt centers of compute power in 5 years time frame. So in 5 years time frame, they want to put all the top 500 systems in one room, basically, and run them that way. So we'll see. I like also the last couple of years, I like to highlight the systems which are not in the top 10, but which are new. So these are the first systems outside the top 10 which are new this November compared to June. And I highlighted the first two. The first two are identical systems installed in Japan at SoftBank. I believe the second and third system in Japan size-wise. SoftBank could have easily decided to combine those systems and submit a combined HPL score. It probably would have been number 11 if they had done that. But it's a very large system, and it's one of those systems which some people would consider in that a hyperscaler market. Anyway, so SoftBank system. The third system I highlight because Chetty, as I already said, is the second module, I believe second module for the first European exascale system. So they are gearing up to produce that system and put it on the list. And it's fairly high already, as it is. And if you look at the computer column, I colored the accelerators. You see that 9 of the 10 systems are actually using NVIDIA technology. Only one of them using the MI300A chip, which actually happens to be another sister system of El Capitan, the one which is installed in Sandia National Labs. Brown is already here on his list. So NVIDIA being very successful in the lower ranks of the list without doubt. So those are the new systems on the list. The next couple of slides, I'm going to be very quick. So the next one is the replacement rate. How many systems fell off the list at the bottom of the list because they are too small? Because the list, we are buying fewer and fewer new systems. We are keeping the systems longer. That's why that replacement rate has gone really down. It was 46, about the same as the last 2 years. That's why in my statistics, I tend to focus now more on the most recent system, not on the old systems in the list. That, as I already said, goes hand in hand with our systems getting older and older. The average system age in the list now is 36 months, meaning 3 years. So if you pick a random system out of the list, it's 3 years, meaning it can be between 0 and 6, really. And we have much older systems in the list. And there is no end to that trend in sight. It hasn't stabilized yet. Quick note on the size of El Capitan. This is the fraction, how much percentage each of the first top 5 systems contributed to the list over the whole history of the list. And you see once in a while, every couple of years, we have really groundbreaking systems which represent a big step in technology forward and represent a large fraction of the list overall. And Frontier was the last one, was the first exascale system, was the last big step up. El Capitan is comparably is a much smaller step up because Aurora and Frontier are in a similar class. So El Capitan is about 15% of the list, but it's not a totally new architecture, totally new generation of systems. And on the corollary, the red and the green dots, which are Frontier and Aurora, they're actually fairly high, probably are the highest they have ever been in the list. So El Capitan is not spectacular like you might have expected, but okay. How much turnover did we have in the list in terms of added performance? Okay, that was actually higher than I expected. It was 30%. Of course, El Capitan makes already up 15% of that, but otherwise there is another 15% coming in new. So that's nice to see. But again, it's in the bandwidth of the recent trend we had seen. And that goes hand in hand with the other effect, which also has stabilized and is not changing, that we see that that accumulation of the system power in the top systems. So the top systems have grown larger and larger compared to the rest of the list, and that trend has not stopped. It's still number 7 is the magic number. The first 7 lists in the top 10 accumulate already half of the performance of all 500, and there is no end to that in sight either. So none of these trends has changed in any way. So with that, this is the traditional slide we put up about performance development. That's HPL performance of the average, the sum, the first and the last system. And over the years now, we have a total aggregate performance of 11.7 exaflops, and the number 1 is 1.7. Entry level 2.3. Okay, so that is a big range actually, 500, almost 1,000. But what we have seen over the years is that we had inflection points due to the end of the NAR scaling. And those inflection points, changing in technologies, they tend to show up, curiously enough, at the bottom first, and with a time delay at the top. And we see another inflection point in 2017 at the bottom, where growth rate had further decreased. We haven't seen that punch through all the way to the top, but it's probably only a question of time. We looked in the past, what is the underlying technological reason for this? And other than what I just showed with power consumption and power budget, the only or the best correlate in our collection of technical data is the total number of cores you have in a system. So this is not the number of cores on a chip, but actually in the whole system. And that one, clearly after 2004, we compensated for the end of the Dennard scaling by doing multi-chips and increasing the number of cores over proportional, but that has come to an end. And since 2017, our system, the core count in our systems globally doesn't grow nearly as much as it has done in the past. It's probably a combination of factors that our chips don't grow the core count as much anymore as they have in the past, as well as that macroscopically our systems in the machine room have reached limits in terms of how many nodes and how many chips we actually want to put in there. And that might tie into that whole power discussion again. The surprising thing for me here is those blue dots actually form a very nice curve. So it seems to be a stable trend, and it seems to be going forward very stable, which of course is my excuse that I immediately take those curves and extrapolate them out into the future. So you see here in blue the number one performance, the performance of the number one system. And if I extrapolate that most recent trend from 2017 out to 2030, you see that most likely we're not going to be having a 10 exaflops. Maybe if some government spends a lot of money, we're going to have that. There might be jumps big enough for that. But performance growth in general is going to be much slower than people expect. Like at the end of the decade, if you have a 10 petaflop system, you're still going to be in the top 500. So with that, I come to the more traditional statistics, 4 slides on where these systems are, who produces them. And I'm going to show one pie chart for the whole list, and after that, I'm just switching to the newest systems. So this is where the system is installed, overall, all 500, mostly in the United States, more than a third. China is still there with 12% of system. That pie is shrinking. China is not giving us any numbers anymore for a couple of years. So those are old systems just aging away. And then you have a mixture of Asian and European countries in terms of number of systems. Now I'm going to focus on the last year and the 95 systems which have been overall in 2020, which we have new in 2024. On the left-hand side, you always see the pie chart if I count number of systems, and on the right-hand side, if I count the installed HPL performance. So the right-hand pie chart is weighted by the RMAX values. In terms of number of systems, it's equal installation numbers in North America, which is mostly the US, Europe, and Asia. If you look at performance, of course, the big systems like El Capitan, they make the blue slice much larger than the other slices. Europe is still a third. There is a couple of new European systems in the top 10, but the Asian systems are not quite, Asia is not quite keeping up with the big systems as much. There's the SoftBank system now and things like that. But in general, Asia, and by that I mean Japan, tends to be on a longer procurement cycle. But once they get a system, once Satoshi gets a new system, he gets a really big one. So that slice in the future might jump back up again, but it might take a while. So if I divide these slices more detail into the countries, you see clearly United States is the main consumer of compute power. But if you rank them by performance, you see Italy is really right now is the country in Europe with a very large influx of new compute power, followed by Switzerland with the upgrade to CSCS, Japan, and then the other European countries. But within a year's time frame, the German slice in the right-hand pie chart probably is going to be much bigger with the first exascale system and things like that. The left-hand pie chart, the number of systems looks more conventional. We can look where these systems are produced, or where the manufacturers are. And of course, most of the manufacturers are in the US. You see its Chinese slice there on the left-hand side. Those are Lenovo systems which are sold outside of China. So those are numbers we get. We just don't get the numbers for installations in China. Okay? But those tend to be smaller systems. That's why in the right-hand pie chart, they don't matter as much. And if I drill that down into the actual companies in these geographic regions, you see in terms of capacity, in terms of performance installed the last year, clearly HPE was the dominating force worldwide. followed by a couple of other companies, Eviden being the leading manufacturer in Europe in this slice. And once the Jülich system comes on, that slice should go back up and things like that. The other one to notice here and to watch in the future is, of course, the red slice, because those are NVIDIA systems manufactured and installed by NVIDIA themselves. So that's a very interesting slice there, too. In terms of chip technology, AMD has contributed a lot the last year, especially for the large systems, like El Capitan. So those are in there. And now I need to do a little disclaimer, a little apology. I was looking for the Intel slice. Why is the Intel slice so small, especially on the next slide? And then I realized Aurora, the first piece of Aurora was installed in 2023. It's 18-month-old, and that's the age we label Aurora forever, when the first piece was installed. So Aurora doesn't count in these statistics. That's why the Intel slice is smaller than it should be. Maybe we can fix that somehow, but of the big three systems, the only one which contributes here is actually El Capitan. So AMD, Intel is clearly still the preferred CPU for a lot of commercial customers. You see that. And in terms of accelerators, clearly NVIDIA is the one which is preferred in a lot of the installations further down the list. And for me, that's not just because they have great products, but also because they have a great software ecosystem. They have all the software stacks and everything. So that's a big selling point for them. But at the very high end, which is the right-hand slice, of course, there is, with El Capitan, there is the AMD GPUs, which got a big chunk. And there is a couple of other systems which are using the MI300s or 250s, which drive that slice up quite a bit. The Intel slice here is missing, as I already said, because Aurora is not counted in these. And the last slide here is the combination of those two. There we go. Where I basically show the combination, what CPU manufacturer and what GPU manufacturer work together. And you see it tends to go all over the place, with the one exception, the big right hand on the right-hand side by performance. And the NVIDIA, total NVIDIA Grace Hopper systems, they tend to be very large and they contribute a lot of performance. The light blue slice AMD, that's El Capitan on similar systems. And on the left-hand side, the big slice is, of course, Intel NVIDIA. Those are the more, I wouldn't say run-of-the-mill, but the more conventional systems installed in the industry. And you see in orange, you also have the AMD NVIDIA combination there. So the highlights, El Capitan is the new #1. We have 3 exascale systems. All of those are at the DOE laboratories in the US. So a very, very nice success for the exascale program. Grace Hopper was one of the new architectures. The MI300A was the other one pushing into the list. And we see a continuation of the more recent trends in technology that growth has slowed down and where that may lead to. Okay, with that, thank you very much.
And with that, I guess we can open it up for questions. If we could have the lights up. There's some microphones in the... You can ask questions to any of the speakers. No questions? Oh, there's one. Yes, please, go ahead.
Thanks for presenting the 2024 picture of TOP500. A couple of questions. One will be the Chinese systems are not here, right? So they have stopped reporting. The other aspect will be a little bit comment on that. Give us a background of, like now we have a segmented world. Number 2, the number of countries who are participating in this top 500. So that also doesn't seem to be growing, limited to 7 or 8 countries, right?
So it's a little hard to hear you with the echo we're getting. Oh. So one was about the Chinese computers.
Kind of, there is a little bit disappointment, right? This is not a global picture, right? So, which it used to be.
Where are the computers? The Chinese supercomputers?
Right, yes, yeah. Yes,
so
yeah.
so you know, we've had conversations with our Chinese colleagues, and they do have very powerful systems, follow-ons to the machines that are currently in the top 500, but they don't want to share the information about the details of those machines. Now, we've seen some papers that have appeared, for instance, the Gordon Bell competitions, where Chinese have entered applications that have been run on the new machines. So we see the specs of some of those machines, and we can understand perhaps what the peak performance is, but we don't have an HPL number. So nothing has been submitted for the benchmarks that we've just talked about. I expect them to, if they did submit, they would be in the top 10. Maybe 3 machines are in China, which could rank in the top 10. But again, the speculation. We only vaguely know about their architectures inadvertently through the papers that have been submitted for the Gordon Bell, or some of the applications that they've submitted papers on. And what was the second question?
The second question is the number of countries who are participating, who are significantly represented in the top 500. That seems to be stagnant over for a while, right? The 7 or 8 countries are showing.
Come closer, and maybe we can have a private, not friend.
Names are significant in the top 500. Seems to be stagnant over quite a few years. About 7 or 8 countries are named here.
So there are 7 or 8 countries which are dominant in the top 500, and those countries are invested in the use of high-performance computing to carry out science industry in their country. So I think that's why the number of countries that appear repeatedly in the top 500 list at the top are the same countries. So I think that's the justification for it.
So the last year or 2 years, there may be two countries to call out. One effect is the Euro HPC initiative and community. They tend to install systems in places where you wouldn't expect it, like Finland, right? So that's one thing. And the other one I noticed this time, and it was I think on some of the slides, is Taiwan installed a lot of systems which in the past they haven't. So sometimes economies all of a sudden step up because there is a financial incentive, there is a need, or there is a government which really supports it. Right? On the same token, I mean, initially China was totally absent from the list, right? And then at some point the government really made it a strategic initiative and built up the industry, and that's how they got in. At some point I would expect that other countries which are developing follow that lead too. I'm still waiting for Indian systems to show up in numbers. And they haven't yet. Yeah? You have seen some effort from South America to get in. They come and go. So we had a couple of years, we had a very constant supply from South Africa, which has gotten a little more quiet recently. So there is some come and go. But as Jack said, at the end it boils down to economic power and financials and stuff like that. Right?
Other questions? Everybody's ready for lunch, dinner, a break? Okay, I guess I should thank everybody for coming to the Top 500 BoF this time. We look forward to seeing you next time. Thank you so much.
Thank you.
And thanks to the speakers.